Okay. Yeah, thank you for having me, and thank you for a nice introduction. So this talk entitled Atomic Embeddability, Cluster Planarity, and Thickenability is joint work with Csaba Todd, whose name I have forgotten to put there, now I see, so I apologize for that. And so this will be a rather a light-weighted, non-technical talk, because that is suitable for this time of the year where many people are taking their days off or might be watching this talk at the beach. And so perhaps so let me start with some history. So most of the mathematical investigations were predated first by some puzzles, and I could identify two puzzles that are very much related to the topic of my talk. So to give a glimpse into this problem that I will be talking about, let's consider this puzzle from the collection of puzzles of Luca Pacioli from roughly 15th century. And so what this puzzle asks us, so we have an enclosure with three houses, and so in this enclosure, so it's somehow separated from the rest of the world by three gates, and we want to connect so house labeled A with a gate labeled A, house B with a gate labeled B, and house C with a gate labeled C. So, and this puzzle, it of course tricks you to think that this is not really possible, right? So why? Because perhaps so it begs you to connect house B with the gate B, right? But once you do it, you can't really connect house C with the gate C or house A with the gate A. So perhaps you can be a bit more clever about it and draw this row that connects gate B with the house B, so that the connection of gate C to the house C is possible, but then you block the connections between gate A and house A, right? So perhaps the best way is to, okay, what about if we first connect house A with the gate A and then house B with the gate B? But that also leads to a dead end. So at this point, solver of this problem, I suspect that this is not possible, that there is no solution, right? However, there is a solution, because the positions of the house A and C inside of this enclosure doesn't really matter, right? So it's just important that there is only one road, namely the one from the house B to the gate B, that somehow separates my enclosure or this area into two parts. So the positions of house A and C doesn't matter, but it's slightly counterintuitive to realize this if you are not used to thinking about this type of problems. So now the second, perhaps more well-known puzzle comes from the 18th century. So the previous puzzle can be conveniently modeled by a graph, by a drawing of a graph where each house and a gate was a vertex, and roads and the fence were the edges, right? So, but in fact, only the 18th century is considered as a starting point of the graph theory, and many literature sources somehow say that this starting point was the Euler's solutions of the Königsberg bridge problem, which asks us to devise a walk through the city of Königsberg that would cross each of the bridges in this town exactly once. Right, so this, of course, we model as a graph. So how exactly do we model this as a graph? So each part of the city that is somehow separated by this river, that will be a vertex, and now we draw an edge through each bridge. And now we want to have a walk in this graph that traverses every edge exactly once. And by Euler theorem, this is possible if and only if there are at most two vertices in this graph, right, that has an odd number of incident edges. So if you have more than two vertices that are incident to an odd number of edges, you cannot have such a walk. So right, I can start. So if you can see, I'm not sure if you can see my cursor or a hand. So you can, let's say, start at this red vertex in the middle, right, and then so you can surely end your walk. Sorry, we have here. Sorry. So what's going on here? Why do we have three? So what's this? So now I'm a bit confused. So I'm contradicting myself because there are now three vertices with degree, or four vertices with degree. So I think this picture is not correct here, but I think it was possible, right?
If I remember correctly, it shouldn't be possible.
It shouldn't be. So yeah, so that's I think that's where my confusion comes from. So we see that here this is not possible. Yes, sorry. Yeah, so I flipped this in my mind, but if you now look at the contemporary version, because the two bridges were destroyed in the meantime, and so now we'll see that this is clearly possible to have a walk in this town now called Kaliningrad that visits every bridge exactly once, because we have two vertices of odd degree, namely the one in the middle and one here in the middle on the right. And so now let me just state formally the mathematical model that we will be working on. So we will consider drawings of graphs, where the graph, so we'll consider simple graphs, so there will be no multiple edges nor loops. So the graph is just a set of vertices with the set of edges that are two element, so is a subset of the set of all two element sets of vertices. And so we'll represent this graph on a two-dimensional surface, right, where each vertex is a distinct point, like in the puzzle from the 15th century, and then each edge is a simple continuous arc that joins its respective endpoints. I mean the endpoints of this edge. And the arcs that connect the edges, they can only interact by properly crossing, right? So we don't allow two edges to overlap or an edge to pass through a vertex. And then, of course, two edges either are completely disjoint or they meet in finitely many proper edge crossings. And so as well as that they can share an end vertex. So this is what we allow, right? So the drawing on the left is fine, and the drawing on the right is not fine. So more formally, we would say that the drawing is just a generic. So we'll work with piecewise linear functions here, so that the drawing is a generic piecewise linear continuous map that is sufficiently generic, meaning that all the self-intersections are immune to perturbations, right? So if we wiggle the drawing a little bit, then we don't get rid of a self-intersection. And so we'll consider crossings as something bad, right? So we don't like crossings like in the first puzzle with the roads, right? We didn't want roads to cross because that can lead to accidents. And so if we are lucky, we can draw a graph on a surface without any crossing. In that case, the mapping will be injective, right? This mapping D from the graph onto the surface or into the surface. And so that's the lucky situation when we get an embedding. So in the plane, the best, of course, that you can hope for is that the graph is planar, right? And there is a nice combinatorial characterization of planar graphs, right? So the graph is planar if it doesn't contain certain forbidden substructure, where these substructures are topological subdivisions. And so here the obstructions are K3, that's a complete bipartite graph with 3 vertices in each part, right? And a complete graph on 5 vertices. So these are the only reasons why a graph is not planar. So we have to have one of these in the graph as a subdivision, as a topological subdivision. So there can be, so we don't have to have exactly them as subgraphs. So of course these edges can be subdivided by vertices. And so these results goes back to 1940s. And so let's see now how this connects with the other puzzle of the Königsberg problem. So now in this talk, we are not only happy if we can draw a graph in a planar way. So we have a planar graph with an additional, let's say, structure, or that we require something more. And what more I will now illustrate on this example on the right. So we have a grid here. And so this grid is a bipartite graph. Some vertices are red, some are blue. And now what we want to now construct is a closed non-self-intersecting curve that has, let's say, red or blue vertices inside and all the other vertices outside. And so this task can be accomplished with the help of Euler's theorem, because what's going on here, right? So we need to look at the plane dual graph here, where in the plane dual, so when I look at an embedding, right, that splits the plane into the region called faces, now I can just put a vertex into each face, which are now these small squares, and then also the outside region or the area that is not covered by the grid, right? So that's the so-called outer face. And now I draw this plane dual just by joining the faces that share an edge, right? So now each face is a vertex, and thanks to the fact that this graph is bipartite, every face has an even number of edges on the boundary, and that means that this dual graph has all the vertices of even degree. Now that allows us to invoke the Euler's theorem, right? That says that if we have a, so now this is the version when we want to have a closed walk that traverses every edge exactly once, which we can do if all the vertices have an even degree, right? So I can now slightly perturb the edges so that it illustrates how this walk that traverses all the edges is constructed. And now by slightly perturbing it, we obtain a closed walk that indeed has, I can now, it's maybe not that easy to see, but once we fill in the interior, right, we'll see that all the red vertices are inside. And so now the question is, of course, why do we care about having all the red vertices inside? And so that I will explain in a second. So first, so in this talk, we are really interested in the algorithmic question of how hard it is or how much time it costs the computer to decide, let's say, if a graph is planar. And then it has been for a long time that we can do this really fast. So this is a simpler, very simple or not. I mean, a problem that can be solved fast for reasonably big instances. But let's say if now we have this additional constraint that some of the vertices are enclosed by a let's say a non-self intersecting curve, as in the instance of the grid that I just showed, right? Then the problem becomes more complicated. Let's say here that there is some practical example where, let's say, we have coroutines of some Python package, and somehow, let's say, each function, or not, it's not coroutine, but some module, right? And each function in this module is a vertex, and now how one module calls the, one function calls the other function or is dependent on it, that's an edge. And now we somehow have this subdivided into sub-modules, right? So now we, of course, want to draw these guys together inside of a nice rectangle, let's say, for better understanding of how this module or a piece of software works internally. And ideally, we don't want to have crossings between dependency edges, right? The dependencies of how one function depends on the other function. And so this can be modeled as the instance of so-called cluster planarity, where so the exact definition might be a bit intimidating, but really what we want is that we have a graph whose vertices are partitioned, right, by, let's say, this partition is now depicted by a color. So these partitions on the right are the submodules, right? All the functions in one submodule have the same color, let's say. And now the dependencies are the edges. And then this partition, it can be also a hierarchical, right? So how you, let's say, if you have a big piece of software, how it somehow breaks down into smaller and smaller pieces is often a hierarchical. So when this hierarchy is somehow captured by how one let's say class or one part of the vertex set should be enclosed in the larger group. Let's say the one that is surrounded by the red disk contains also those guys that belong to this blue disk here. And now, so we just want to draw these whole things that there are no unnecessary crossings between edges and the boundaries of these disks. And we will see soon that this somehow naturally can be generalized to a very, let's say, natural problem of the so-called thickenability. But at this point, we are still in the plane, right? So what we have here, so we want to draw our planar graph so that there are no edge crossings. So there are still no edge crossings. This is important here. And so that there are no unnecessarily crossings between these disks or the boundaries of the disks, right? And the edges. And so then when you just state what I was just talking about, formally you get this, right? So we have a problem where we have some input graph whose vertices are partitioned by this map mu. So this is a hierarchical partitioning, perhaps. And so yeah, this is perhaps the most technical part of the talk. So sorry if this is too hard to digest, but pretty much what we want to output, yes or no. Does there exist an embedding such that the intersections between the boundaries of the disks in C with the edges with each edge is at most one, right? In 1 point. So let me know if there is a question at this point. So perhaps let's illustrate this by an example. So here we have a simple instance, which is a graph, which is the complete graph on 5 vertices, if I'm not mistaken, whose vertices were partitioned into 2 parts. And now, if we want to respect this partition, and we don't want to create any edge crossing, then there must be an edge that creates an unnecessary crossing with this ellipse on the right? So either this edge that goes around this red edge, either it creates a crossing with some other edge, or it will cross a boundary of this disk twice. So this is a negative instance, right? So this collection. So in this particular case, we have 2 curves in the collection C of a pairwise disjoint simple closed curve that somehow defines this hierarchy implicitly, how one curve is contained in the other curve. So here we are still in the plane, so we can naturally define an inclusion partial order on these curves. So if there aren't any questions at this point, which so let me have a bit of water. Okay, so now let's see. So how does this relate to other similar problems? So there is a whole zoo of similar problems that are mostly studied due to the goal of finding a good way how to make a software for automated drawing of graphs. And so this investigations is also widely theoretical. So we just want to see which of these problems are hard, meaning NP hard or NP complete, and which are polynomially time solvable. And now, so what this diagram signifies is that here at the top, the standard, we have a standard planarity testing, and then whenever we have an arrow to another node, this means that this more constrained planarity testing, right? It can be used as a black box to solve the other planarity testing, or in other words, the standard planarity testing can be reduced to some some richer planarity testing with some constraint. And so where we are here now is that, so we are now at this clustered planarity, which wasn't known to be polynomial or NP hard. And pretty much all of these problems in this river of uncertainty are, we didn't know whether they are polynomial or not. Now, so with this resolution, now pretty much only this problem, simultaneous, this CFIT2 problem is the last sort of well-known problem in this area whose tractability status is unknown. And that would pretty much close this like a basic fundamental branch of algorithmic research. So here, of course, at the top, this P means that all these problems are polynomially time solvable. So this gives some kind of a brief overview of the zoo of all of these problems. And so there, here at the bottom, we have those that are NP hard, if that wasn't clear. And just a little bit of history. So this problem was open for about 25 years, was introduced in 1995 by Feng, Cohen, and Eades, and others considered all very similar variants. Was somehow open already when the graph was quite simple, was a path or a cycle, and there were some special cases identified that, but let's skip to the main result. So here we gave an algorithm with the running time of n to the power of 8 that was already improved to a quadratic running time. And so perhaps one of the reasons why this wasn't solved earlier is that often a problem cannot be just solved if you just look at many special cases. So in this case, it was somehow better to solve a more general problem, right? So because it is just hard to solve this clustered planarity without that wouldn't also solve the problem of thickenability that I will talk about in a bit. And I also believe that already the very simple case when the graph is just a cycle and we partition the vertices of this cycle into 4 parts, it contains all the difficulty of the problem. That means that I don't see any solution that would solve this very simple case that already wouldn't resolve the whole thickenability problem. And so let's look at why just cycle is already interesting. So let's see that in the original planarity, right? So what we don't want, we didn't want to have K-free as a subgraph. And that, let's say if now I just have a cycle with 6 vertices, in each part there are 2 vertices, right? So now this partition is encoded by colors. So now if we want to have each color inside of its own disk, we better are able to connect the 2 blue vertices, 2 red vertices, and 2 green vertices by an edge in a way that they don't cross these edges, right? But of course, once we draw it, we get K-free. But unlike in the case of the classical planarity testing, we cannot really reasonably identify simple abstractions like some simple substructure that once we find it in the graph, then we can say that this instance is negative, because I can just add more vertices here into this instance just by subdividing the edges, and then I still have some kind of a k-free there, but suddenly the instance is positive because I'm not forced to connect a particular pair of blue or red and green vertices. I need to just add more edges in so that the subgraph that is induced by the red guys is connected, the subgraph that is induced by the blue guys is connected, and the subgraph that is now I don't know which color I haven't mentioned, but so that the guys of each color are connected, and no, there are no more edge crossings, right? So and once I do it, I can draw these meanders sort of to enclose vertices of the same color inside of a disk. And perhaps this should have been a hint that this problem is really has something to do with meanders, right? And they appear in the study of three-dimensional manifolds. And this is like why this problem just could not have been solved without considering a bigger picture here. So what is this bigger picture? So that's considering two-dimensional simplicial complexes and how they embed in 3 dimensions, right? So the graph was just a one-dimensional pure simplicial complex that was somehow just so in the abstract way was just a set of 2-element sets of vertices. Now we'll need to consider 2-dimensional creatures, which I can just restrict myself to 2-dimensional pure simplicial complexes, where now all the combinatorial information that we are interested in are which triples, which unordered triples of vertices are in my set or in my simplicial complex. And then all the edges that bound these triangles must be there too. And now we want to now assemble this in this 2-dimensional simplicial complex and 3D. Right, so this can be often achieved. So what we are doing here, we have some kind of a Lego type deal, right, where each piece is a triangle, and now we want to glue this triangle together along edges, right, while preserving the labels at vertices here, right? So if we have these 3 components, 3 triangles, we can easily assemble them in 3D. We can add we can even add another triangle, and now we can still assemble it in 3 dimensions. Now let's say if we take a K5 and we look at all the triangles that share an edge with the K5, and as well as so all these triangles share one vertex and then also contain one edge from the K5. This is what I meant. Then it is not that hard to see that if now I want to have a triangle about each edge in K5, so that there is no 3-dimensional manifold that will allow me to do this without creating some crossing between triangles. Here by crossing, I mean a common point, but that is not the boundary point of both triangles. And
sorry, a short question.
Yeah.
In this assembling, you really want things to be straight? Or
no,
do you allow?
Yes, that's a good question. Yeah, we want to assemble it in any, so we can curve this triangle. They are made from the very good rubber that can stretch and bend as much as we want. So, And then other problem comes from knots. And these knots and links make this assembling problem MP hard. But what if our simplicial complex is simply connected, right? That we cannot, every curve inside of it can be contracted into a point, right? So can we decide efficiently whether we can embed this in 3-dimensional, in let's say R3? Or in a more general way, in any manifold, right, that is a 3-dimensional and orientable. So here, let's say I will just restrict myself to 3-dimensional orientable manifolds. So here we have the problem of thickenability. So we have a 2-dimensional simplicial complex, and now we want to ask, can this be embedded into some orientable 3-dimensional manifold, right? That's in a space where no matter where you are, your neighborhood looks like a 3-dimensional space. And there is some kind of a consistent orientation here. So a prototypical negative instance besides this K5 with like a cone over K5 that I just showed is a Möbius band with a disk attached along its middle circle. And so now the question is, so is this problem polynomially time solvable, or you pretty much have to try all the combinatorial possibilities of how to glue the triangles, or how to somehow, sorry, no, how to decide the order of the triangles along an edge, roughly speaking. And so from by the results of Neuwirth from 1968, the thickenability was known to be in MP due to what I just said. So Neuwirth just proved that it is all about the order of the triangles around the edges, right? So we just need to find some kind of a compatible ordering of triangles along each edge that somehow leads to a nice combinatorial property, which is that each link is planar. And so now a link, right, in this 2-dimensional object is a graph where we turn, so we just look at all the triangles incident to a vertex, and then we convert each triangle to an edge, or sort of we grow a small sphere around my vertex and intersect my simplicial complex in a hypothetical embedding, right, in a graph. Because when I'm intersecting two-dimensional things, namely triangles and a sphere. So if the thing is sufficiently generic, I get a graph in the intersection. So now here at the bottom, we see this link of the vertex V of the complex here, right? So here we see that vertex V is incident to 5 triangles. That's why its link has 5 edges. And this link must be planar if we have an embedding in a 3-dimensional manifold. And that's where the connection with C-planarity comes from. And now, so these cyclic orders or compatible cyclic orders of triangles just pretty much translate into a planarity testing problem with some constraints. So we want to pretty much test if all of these links can be simultaneously embedded in the plane, so that for every edge, when I just look at an edge UV, right, this edge UV has or gives rise to two vertices in two links. And now when I look at this embedding, I want to have the cyclic order of the edges. Let's say at if I have an edge UV, so I want to have the cyclic order at U2 to be opposite of the cyclic order of the edges that come from the same triangles, right, at V. Because when I have an edge, right, so both endpoints see the same triangles incident to this edge in the two-dimensional complex. And this Neuwirth's theorem says that yes, that this sort of necessary condition is sufficient. But furthermore, if my simplicial complex is simply connected, that means that every closed curve is contractible to a point within this complex. Then it tests whether, in fact, the two-dimensional complex embeds in R3, right? So that's perhaps a more tangible question, right? So, but that we need to just restrict ourselves to this special class of simply connected complexes. And this was, in fact, the question that was asked several times in the past, right? So can we test embeddability of two-dimensional simplicial complexes in R3 if they are simply connected? And so by our result that, so let me skip this connection here because we are running out of time. The answer is yes. And in fact, our result so came out roughly at the same time. So in fact, there was some communication between us and Karmesin, who was looking at the Kuratowski style characterization for thickenable two-dimensional simplicial complexes at the time. And then, though his main goal wasn't to give an algorithm, but he claimed an algorithm for pretty much thickenability testing. But to the date, I'm not sure if this result was verified. And so our contribution was also the simplification of the machinery so that it could be then pretty much just the whole problem can be expressed in purely graph theoretical terms, which then was later taken an advantage of by Ignaz Ruther et al., who reduced the running time to n², which is really now the case, but I'm not really sure what happened with this manuscript of Karmesin, which was about 50 pages or more long. So I'm not really sure what is the status of this now. Yes, so if there aren't any questions. So here for like, why I got into this business was to pretty much resolve the complexity status of all of these problems in this diagram. And now what really remains is just to test whether two planar graphs can be simultaneously embedded, which I'm not going to describe formally, but most likely just I can say that this problem should be polynomially time solvable, but it seems that there are still some ideas needed to come from the thickenability to this problem. Okay, so that's all from me.
All right, thank you very much.
Thanks.
Do we have any questions?
Can you go back to the slide with the Neuforth theorem?
Sorry?
Can you go back a few slides with this theorem about thickenability from 1969?
1960, yes. Yeah.
No,
68.
later, 68, yes. So here it says that thickenability is NP, but then later you prove that there is an algorithm which is quadratic in N. So
Yeah.
what's the difference?
So NP means that it can be still polynomial. So NP is non-deterministic polynomial,
Oh,
which is like a strictly larger complexity class.
Yeah.
And it's not
okay, I
NP
see. Yeah.
complete. It's not, if you show that it's NP complete and polynomial, that would be.
Yeah, I see. I see. And yeah, and maybe you talked about it, but how do you reduce the what's the reduction between this clustering problem and thickenability?
So basically it is here. So we can see it as a, so we can see thickenability of a graph and embeddability problems that we dubbed atomic embeddability, where we somehow have some kind of an atomium where each ball or each sphere in this atomium is sitting or has a vertex of the complex at its center. And then we have a link embedded on each of these spheres that are centered at vertices. And now I can just drill out, in fact, the vertices on these spheres and pipe them, right? So, and now reconnect the severed edges along the pipes that, so each pipe corresponds to an edge in the simplicial complex, right? And then all the triangles that share this edge have a curve that passes through this pipe. So we get some kind of an atomium. And now we just want to find an embedding of this whole thing, where now I need to introduce some vertices here. They can be just vertices that are subdividing these curves such that each curve visits 3 spheres and has 3 vertices all together, right? So each of this curve is sort of a closed curve. And now we want to draw all of these curves on this atomium without crossings. And that's somehow some problem that is more general than cluster planarity, if this makes sense.
It just seems that you reduced it the other way around. You reduced thickenability to this more general problem, which looks like clustering.
That's yes, that's a good point. But yes, this is the, in fact, they are polynomially equivalent. Yes, you are right. This is the other direction. Okay. And like similarly, you can, what I stated here, clustered planarity can be reduced to, yes, you can, yes, you are right. You can cook up an instance of like a 2-dimensional simplicial complex that is simply connected, and not necessarily simply connected, that is thickenable if and only if this instance was C-planar. So it's, yes, sorry, you are right. There is another
okay.
instance, like a way how to do it. Yeah. This is not, this is exactly the opposite way.
Okay.
Yeah.
Are there any other questions? So I have a small one. So you now give an algorithm which tests cluster planarity. Can you somehow turn this into an algorithm that actually gives you a cluster drawing?
Yes, yes.
Okay.
Yeah, so it's basically is the same complexity. I mean, with this new algorithm of Ignatz, Rutter and company, which I believe is correct, though it didn't appear in any journal, but I believe it's correct. You can very easily convert it into an actual drawing.
Thanks. Are there any other questions? That does not seem to be the case. So thank you again, Ado, for the talk and the discussion.